Hello, viewer. Myself, Dr. Ishad Ahmed Khan from Department of Mechanical Engineering, Sagar Institute of Research and Technology, Bhopal. Today we will discuss column and struts, and both are the very important member of a structure. Let's understand what is column, and we are also know column known as a pillar. So, what is this? Let's understand. So that pillar or column is a architecture and structural engineering is a structural element that transmit through compression the weight of the structure above to other structural element below. In other word, a column is a compressive member, or easily we can understand a simple example by a simple word. We can say that the vertical element of a structure is subjected to the compressive load. It's said to be, or we can say it is a column. And next thing is that strut. So strut is a structural member which is subjected to axial compressive force. A strut may be horizontal, vertical, or inclined with any end fixity condition. Connecting rod and piston rod, which is an example of strut. So let's see the few more example of strut with a diagram we can see. So this inclined structure. This is called a strut, and here also this element is called as strut. So hope you understood what is the strut. So the next important thing, the how the failure occur in a column. So the failure occur in the column due to stresses set up in the column. So following stress may the reason of the failure of an strut, which are direct compressive stresses, buckling stresses, and combined of direct compressive stress or the buckling stresses. The mode of failure of a column depend upon its length and depend on the mode of failure. A mode of failure of a column are classified as short column or long column. Okay, so we can classify it as two types. So let's understand what is the difference between these two. So column whose lateral dimension is very small with compared to its length or height. So my dear students, we can understand with, like, suppose this is a length. If this length means this is the length of the column. So if this part, this length, what I'm telling you, this is let more than this dimension in lateral dimension. So it's said to be a long column. And an opposite of that, we can understand if the lateral dimensions is very large as compared to the length of the column. So something you can understand with we can understand with that. Okay, so like suppose some block kind of structure is there. If this dimension is like this and this, so if this type of structure is there, so you can see this is comes considered as the short column. See, lateral dimension is larger than this height. Okay, so we can you can understand easily with this diagram. So generally, we can say a long column failed by the buckling and short column failed by crushing, because the short column have less, very lateral dimension is higher than longitudinal one, so it fell by crushing. The ratio of effective length to least radius, the least lateral dimension is greater than 12, so it can considered as a long column. And the ratio of effective length to least lateral dimension is less than 12, so it can consider as a short column. So lateral dimensions we can understand. What I think you already we had discussed in the previous classes. And so let's see that if this is a circular kind of structural element, so this is called the lateral dimension, and this one is called the longitudinal dimension and toward the length. So if this ratio, the effective length, this effective length to the least radius of least lateral dimension is less than 12, so it's considered short. If it is greater, it's considered as the long column. Okay, slenderness ratio is greater than 45, and so it is considered as a long, and if it is less than, so it is considered as a short column. So slenderness ratio, what is that? And slenderness ratio, it is the effective length ratio of effective length to the radius of gyration. So we can say it's a slenderness ratio. As the height of column increase, the load carrying capacity is less. As the height of column is decreased, the load carrying capacity is more. You can understand. It's simple. So radius of gyration is less and radius of gyration is high. Yeah, of course, radius of gyration is lateral dimension. So this simple thing we can understand. So it may be it high in case of the short column, and the load carrying capacity is less and load carrying capacity is more. Okay, so long column is subjected to buckling stress and short column is subjected to compressive stress. Okay, we can understand this because if it is you can take example of this. You can see this is a pin, and suppose this is if you apply the load, so it may failure after first it's a buckle and then maybe failure, because you can see that this dimension is quite higher than this lateral dimension, so you can say this case is a long one. Okay, so in this case we can understand so how buckling occur. Okay, suppose we can take out a refill and we apply the four at the board end condition. So first it's a buckle. Buckle means it is like this. Okay, we can understand that we can see that with the help of diagram. So I'll show you in the coming slide. So let's understand what is the slenderness ratio. So slenderness ratio is nothing but this is the formula of Euler load formula, and P upon pi square EILE square, and where the is the area and this A is the area. It should be capital A, and K is the radius of gyration. So in the coming classes, we definitely will discuss derive the formula of Euler for different end condition. Today you can just write, you can understand and you can just see this is the formula, and we can rearrange this. So this term LE upon K, that is called the LE upon K. This term is called a slenderness ratio. Okay, so this term is called as slenderness ratio, and this should not required actually. So the ratio of LE upon K, that is called a slenderness ratio. Hope you understood with this. So let erase on all and come to the next slide. So Euler's theory for the column. So before applying the Euler theory, we have to take some assumptions and the sign convention we have to consider. Then we can move on the Euler theory for the column. So assumptions is that initially column is perfectly straight and load is axial. So we have to assume initially the which column where we are applying the Euler theory, Euler column theory. So there must be a state and load, and which load is you applying, it must be axial loading. Cross section is uniform throughout. There is no distortion and there is no change in the cross section. Column is perfectly elastic, homogeneous, isotopic, and length is very long as compared to the cross section, and failure for the column occur due to the buckling. So these assumptions we have to be considered for the Euler theory. If we are interested to calculate the Euler load, buckling load, you can say. And this simple two diagram, you can see that it is the nomenclature. No, sorry, it is for the sign convention what we are going to be following in the coming classes. So if this concavity stuff, if this type of buckling occur, concavity is made of like this, so we can take the sign as a negative. And if this type of the buckling of column occur, so we have we should take the positive, and this is come under the you can say this is convexity at the center is occur, so this is taken the positive sign. Okay, some end conditions we have uh, take in this case. So first one is in for the Euler loading condition, your to derive the Euler formula, Euler load, we have to take a few popular end condition, and which are, so first one is that this is one end fixed and another is a free. So in this case, this is called the effective length, and effective length would be equal to the 2 times of the actual length of the column. So effective length, how it is calculated? So you can say when deflection is start at the end, you can meet by the straight line. So to get this, the straight line, if you draw here in this way, so you have to be increased this time, so it's become 2 times of that applied, initial one. So here L is equal to 2L, and these things we can get from the Euler formula also, so we will discuss in the coming classes. So let's see the both end fix. If the both end fix and you apply a load here, so this condition, the effective length and the original length is equal, and one end is pinned and one end fixed, so it would like this. So it is because of 0.7 L, or we can say the root L upon root 2, and if usko solve karenge, so we will get the 0.7 L. So and the both end fixed, so in this case, so L is equal to half L, or L is equal to L by 2. This is the end condition. So thank you so much for being listening patiently. And this is a very basic information about the column and strut. And from coming class, we will discuss the Euler formula for different end condition. Thank you. Thank you so much.